Okay, very good morning, my dear students. In the last class, we calculated the probability of error for binary ASK system and binary PSK. And we concluded that the probability of error for binary PSK system is almost all half to that of binary ASK system. So in the today's session, we can discuss the probability of error for BFSK so that we can compare the three techniques in terms of the probability of error as well as the output SNR. Okay, so in the today's session, we can calculate the output SNR and probability of error for binary FSK system. See, almost all we have followed the same procedure for matched filter, binary ASK and binary FSK systems, as well as binary PSK. So in the same fashion, we can go through the probability of error calculation for binary FSK. First, we can calculate the square of output SNR. First, we can calculate the square of output SNR, and then please wait 1 second. First of all, we can calculate the square of output SNR, and then we can calculate the output SNR using that by applying a root to the rho max. So after then, we can substitute the same value in the probability of error, that is the output SNR, so that you can extract the BFSK. And always remember that here the square of output SNR should be maximized. Okay, follow the same steps as we discussed in the last class. So first step, what is the first step? So make use of optimum filter and take the probability of error expression for optimum filter. Okay, so consider it. If you consider it, you can see what is the expression for probability of error. It is half ERFC of x01 of t minus x02 of t divided by 2 root 2 sigma. So what is x01 of t minus x02 of t? It is nothing but the square of output SNR. It is the square of output SNR divided by sigma whole square will be the square of output SNR, and x01 of t minus x02 of t is specifically the change in the output signal. So the change in the output signal is defined as x0 of t, x0 of t, which is x01 of t minus x02 of t, and a sigma represents the standard deviation. So a sigma square will be the variance of the output noise component. So that's why we can say that this ratio is the signal to output SNR. This ratio is the output SNR, and we are considering the square of output SNR. So we are going to maximize that. So because here the relationship between PE and output SNR is ERFC of output SNR. So it means that there exists the complement relationship between the probability of error and output SNR. Okay, so rho max will be x0 of t divided by sigma whole square. Once you maximize this, automatically you can reduce the probability of error because there exists a complement relationship between the probability of error and output SNR. So rho max will be x0 of t divided by sigma whole square. Already we calculated in the module 2 and we obtained the square of output SNR for optimum filter as integral minus infinite to plus infinite mod x of f square divided by SNI of f dm. Okay, so whenever the input noise PSD is white in nature, so we assumed that the Gaussian noise is assumed to be white in nature. So that's mean that it will have uniform power spectral distribution. It will have uniform power spectral distribution, and that input noise Fourier transform is assumed to be as N0 by 2 because the noise is almost all like blunt bell-shaped distribution you will get. So that's why SNI of f will be N0 by 2, where SNI of f is the PSD of input noise, or you can say the Fourier transform of input noise. Please once again replace the square of output SNR expression by using SNI of f as N0 by 2. And please substitute SNI of f as N0 by 2, and you will, because this is down to the denominator, so you will get it as 2 by N0 integral minus infinite to plus infinite mod x of f square df. Okay, so just we took the SNI of f value N0 by 2 to the numerator, so that we will get 2 by N0 integral minus infinite to plus infinite mod x of f square df. Okay, Now, as usual, so the same steps we are following. What next? We should replace the mod x of f square df. That is the square of magnitude of integration of a particular function in frequency domain and in time domain. Both the magnitudes are equal. So that's why we can replace mod x of f square df by using Parseval's theorem. And we are going to integrate for a bit interval because this is a binary FSK. So your binary represents that only one bit is transmitted per, like only one bit is accumulated in a one particular symbol. So that's why we can say that the integration limits are from 0 to TB. And we are applying Parseval's theorem to the square of output SNR expression. You will get 2 by n naught integral 0 to TB, and we'll replace x of f square df as magnitude of x of t square dt. Okay, and already I told you that x of t is a change in the input signal. X of t is a change in the input signal, which is, so that's why you can say that it is the difference between the positive magnitude and negative magnitude of the input signal. So you can say that it is the difference between the two magnitudes, the positive magnitude of the input and negative magnitude of the input. So that's why, as usual, we'll replace the x of t. What is x of t? Change in the input signal. That is x1 of t minus x2 of t. So just to substitute x of t as x1 of t minus x2 of t square dt. So almost all the derivation is same for all the systems up to this equation. So up to this equation, almost all the derivation steps that you should follow. What is the first step? First, take the output probability of error expression for optimum filter and define rho max, which is square of output SNR. And in that, please replace mod x of f square df as mod x of t square dt using Parseval's theorem. And replace input noise power spectral density as n naught by 2. And x of t is the change in the input signal. So that's why you can define it as x1 of t minus x2 of t. So up to this point, the same steps we have followed for all the derivations. Okay, now from this you will get some change. You can see that one. So what next we'll do? We'll consider the general BFSK signal. Okay, already you know what is binary FSK. So binary FSK is a change in the frequency of sinusoidal carrier, change in the carrier frequency, or else you can say that change in the carrier frequency with respect to instantaneous values of input signal. But the input signal has two levels, 0 and 1. And always, and one more thing that you should recollect is that in BFSK, we consider the input as unipolar only. Okay, so in only BPSK, that is binary phase shift keying, we consider a bipolar signal. But other than PSK, that is in the case of either ASK or FSK, we used unipolar signaling format for the input signal. Okay, so positive signal. So that's why we are going to divide the define the positive magnitude signal and negative magnitude signal. See here, positive magnitude represents that the signal, that is the modulated signal, BFSK modulated signal for the data bit 1. And for the data bit 0, we are defining as negative magnitude. But actually here we don't get negative magnitude. Here we'll get only change in the carrier frequency. Here we'll get only the change in carrier frequency. Here we'll get only the change in the carrier frequency. So that's why here x1 of t is the increase in the carrier frequency whenever the input data bit is 1. And whenever the data bit is 0, there is a decrease in carrier frequency. So by an amount of defined this analog omega. Okay. So omega c plus this omega value. Okay. And similarly, there is a reduction in the carrier frequency for data bit 0. So that's why we have defined x1 of 2 and x1 of t and x2 of t as two frequency components respectively for the data bit 1 and data bit 0. So I think you can know the definition for x1 like BFSK signal. It is there is a increase in the carrier frequency by an amount of omega for data bit 1 and there is a decrease, that's why we represented with negative sign. So decrease in the carrier frequency by an amount of omega for data bit 0. Okay, now please substitute the values of x1 of t and x2 of t in the square of output SNR. Already we defined the square of output SNR, rho max. How we defined rho max? 2 by n naught integral 0 to tb x1 of t minus x2 of t whole square. x1 of t minus x2 of t whole square. Now just directly you substitute the value of x1 of t. Please wait for 1 second. Please substitute the values of x1 of t and x2 of t. What is x1 of t? Root over, please wait. So root over 2 ps cos omega ct root over 2 ps cos omega c plus omega divided into t, and similarly if it is negative magnitude you will have, if it is negative magnitude you will have root 2 ps cos omega c minus omega multiplied by t. So that is the decrease in the carrier frequency. Now please substitute x1 of t and x2 of t in the square of output SNR. This is x1 minus actually here you will get minus, but I represented it as positive. So please you write down x1 of t minus x2 of t whole square. What is x1 of t? x1 of t is root 2 ps cos omega c plus omega multiplied by t, and x2 of t is, okay, here you got this minus, so please keep it as negative. Please take it as negative. Okay, actually I did some mistake here, negative. Okay, so root 2 by n naught integral 0 to tb, 2 by n naught integral 0 to tb, here you can see. You can write like this, 2 by n naught root 2 ps cos omega ct plus omega minus root 2 ps cos omega c minus omega multiplied by t. Okay, please substitute like that and take root 2 ps as common. Take root 2 ps outside the square. Then what will happen? The square and the root gets cancelled. The square and a root gets cancelled. Okay, you can see here. Take root 2 ps outside the square so that root and square gets cancelled, and you will get finally, you can take that root 2 ps outside and 2 by n naught multiplied by 2 ps. So you will get it as 4 ps by n naught. 4 ps by n naught. Please all of the students substitute the value of x1 of t and x2 of t in the expression. Okay, so that's all. Actually I kept negative. So instead of negative I kept positive. Here you can see. Now you can check here. So I substitute the value of positive and negative magnitudes of a BFSK signal in the square of output SNR. Then you will get 2 by n naught integral 0 to tb root 2 ps cos of omega c plus analog omega multiplied by t minus, why minus? Because x1 of t minus x2 of t. Here this is x2 of t. So I substituted x1 of t and x2 of t, where x1 of t is the BFSK signal for data bit 0 and x2 of t is the BFSK signal for like a change in the decrease in the carrier frequency for data 0. Please substitute here and please take root 2 ps as common from these two. If you observe these two, you can observe that you can analyze that root 2 ps you can take it as common, that is common term. So take it out. So square and root gets cancelled. So you will get 2 PS now outside the square. So take, because it is independent of time, you can take it out. So then you will get 4 PS by N naught integral 0 to TB cos omega C plus omega multiplied by T minus cos omega C minus omega multiplied by T whole square. You can see that here. So 4 PS by N naught integral 0 to TB cos omega C plus omega multiplied by T minus cos omega C minus omega multiplied by whole square dt. But from the trigonometric expressions, certain trigonometric expressions, cos A minus B minus cos A plus B, cos A minus B minus cos A plus B is 2 sin A into sin B. Okay, but actually here you have cos A plus B minus cos A minus B. That's why I took it as minus 2 sin A sin B. 2 sin A sin B. That's why we got negative. Okay, why we represented that using trigonometric expression. Cos A minus B minus cos A plus B is 2 sin A sin B. 2 sin A sin B. But here you have cos A plus B minus cos A minus B. So that's why you can write it as minus 2 sin A minus 2 sin A into sin B. Okay, we have magnitude square. That's why as usual I kept the magnitude square into dt. Now it is 4 PS by N naught integral 0 to TB minus 2 sin omega CT into sin change in this omega is a small value. Remember that omega, analog omega component is a change in the frequency, that is like very less value compared to our carrier frequency omega C. Okay, the change in the carrier frequency omega is always less than the carrier frequency omega C. Okay, so now you have magnitude square. So if you so negative term gets cancelled because minus 2 whole square will be 2 square only. So you will get 4 here. So if you take that 4 outside the integration, you will get 16 PS divided by N naught. 16 PS divided by N naught integral 0 to TB sin square omega CT into sin square omega T dt. Okay. Now so once again use certain trigonometric equations. This is sin square omega CT. So you can write this as 1 minus cos 2 omega CT divided by 2. And once again you have change in the carrier frequency, that is omega. So sin square omega T, ohm T. So that omega is nothing but 1 minus cos 2 omega T divided by 2 into dt. Now in the output section, generally you will have a receiver at the output receiver section, you will have a low pass filter. Now our signal component should be allowed through the low pass filter. So once we allow this whole signal component towards the low pass filter, because in the low pass filter you have a shunt capacitor. So what that shunt capacitor will do, capacitor allows the higher frequency component. Okay, so because the capacitor is connected in shunt, what it will do, it will bypasses all the high frequency component towards the ground. And what it will do, it will allow only the low frequencies to the output section. Now if you carefully observe this equation, you can find that 2 omega CT component is a higher frequency component, because you know that omega C is a carrier frequency which is always a high frequency component, and obviously 2 omega C will be much more higher value. And what about this omega T? This omega is a very less value, change in the frequency. Okay, that is very less value, and 2 omega will also be less value only. Okay, compared to omega C. So almost all this omega will be nearer to omega m, like that. It is in the range of kilohertz, and our omega C will be in the range of megahertz. So that's why once the component is applied to the low pass filter, higher frequency components, okay, the component higher frequency components will be eliminated. So cos 2 omega ct will be eliminated. So you will get only DC component, that is 1 by 2. And what is one more thing? 1 minus cos 2 omega t by 2. This factor will be allowed by the low pass filter, being this omega as a change in the frequency, which is very low value compared to carrier frequency. Okay. So that's why you can eliminate this factor. Which factor? Cos 2 omega ct. Okay. Let us move to the next slide. So if you observe the simplification, once the component is applied to the low pass filter, already I told you that higher frequencies 2 omega c will be eliminated. Then the square of output SNR, will be rho max is equal to same 16 PS by N naught integral 0 to TB half. Why? Because we eliminated cos 2 omega ct, half into 1 minus cos 2 omega t divided by 2 dt. Okay. Now this rho max, please simplify this expression. Here in the denominator you have 4, 2 into 2, 4. So numerator you have 16. So you will get 4 in the numerator. So 4 PS by N naught, integral 0 to TB, 1 minus cos 2 omega t dt. 1 minus cos 2 omega t dt you will get. So it is equal to 4 PS by N naught, Now please observe this equation. What is the, see here you have two terms, one is 1 and other is cos 2 omega t. Now if you integrate this 1 dt, you will get t as a first term, and if you apply the limits it will be TB minus 0. So that's why I directly represented TB here. So what is the integration of first term and applying the limits from 0 to TB, you will get it as TB. That is the bit duration, minus here cos 2 omega t. So integration of that will be sin 2 omega t divided by 2 omega t multiplied by you will get TB. Okay. So that's why I represented TB here, sin 2 omega capital TB divided by 2 omega capital TB. We applied the limits. So the integration will be like this. Now, here please take TB as, like you can take TB as common. Okay, take this T suffix B, which is the bit duration, as common from these two terms. If you take TB as common, you will get 4 PS into TB divided by N naught into 1 minus sin 2 omega TB divided by 2 omega TB divided by 2 omega TB. Now please apply 2 omega TB as 3 pi by 2. Why we are replacing 2 omega TB as 3 pi by 2? Because once you do like that, you can maximize the square of output SNR. Here, in order to take TB as common, we represented TB in the denominator. In order to, if you multiply these two, what here will do? TB gets cancelled and you will get the integration of cos 2 omega t directly. So 4 PS into TB divided by N naught into 1 minus sin 2 omega TB divided by 2 omega TB. Now the square of the output SNR, you should maximize that factor, because our intention is to reduce the probability of error. So in order to reduce the probability of error, kindly take 2 omega TB as 3 pi by 2. Then you can say that the square of output SNR can be maximized. So you can apply different values. You can apply 2 omega TB as pi by 2, and you can apply 2 omega TB as 0. Okay. Like that you can, like in order to maximize the value, not like infinite, in order to maximize within a certain limit, then you can consider 2 omega TB as 3 pi by 2. You can also consider it as pi. So if you consider as pi, you will get less value compared to the value 2 omega TB as 3 pi by 2. So that's why I directly substituted 2 omega TB as 3 pi by 2 to maximize the square of output SNR rho max. So that's why rho max will be 4 PS TB by N naught. See, you may get a doubt. Can we replace with respect to pi or another values like 0 or any other values? But you will get maximized value only when 2 omega TB is 3 pi by 2. Okay, that's why I directly substituted like 1 minus sine 3 pi by 2 divided by 3 pi by 2. So if you take pi as, this is not in radians, this is in degrees. So 3 pi by 2, it will be, so here this is 3.14 actually. So if you substitute, you will get 4.712. And if it is angle, it will be 3 into 180 divided by 2. That's, you will get 270. So sine 270 degrees will be minus 1. So 1 minus 1 by 4.712. Okay. Now let us move to the next slide. So what we did here, directly we calculated the rho max value, but here in order to maximize the square of output SNR, we considered 2 omega TB as 3 pi by 2. Just directly we substituted the value and we got 4 PS TB divided by N naught into 1 minus 1 by 4.712. So we can simplify the equation further. So if you simplify the equation, so upon substituting 2 omega TB as 3 pi by 2, you can maximize the square of output SNR. So you will get 4 PS TB divided by N naught into 1 plus 0.21. So if you take that value, you will get like this. So this is 1.21 multiplied by 4. So you will get 4.84 PS TB by N naught. Okay, the same value I mentioned here. So what is the square of output SNR in the case of BFSK? 4.84 EB. Because here EB is the bit energy, you can replace EB as PS into TB. So that's why I directly represented bit energy as PS into TB. So but the output SNR can be obtained by taking the square root of rho max. Then output SNR rho max will be, root rho max. That will be x01 of t minus x02 of t by sigma, because actually rho max is square of this value. So root rho max will be change in the output signal divided by change in the noise component. Okay, so this will be directly if you take, so directly if you observe here, it will be root rho max. So root over 4.84 PS into TB divided by N naught. 4.84 PS into TB divided by N naught. So we replaced EB as PS into TB, then you will get it as root over 4.84 EB by N naught. What is EB? EB is the bit energy, which is PS into TB. Now the output SNR. So finally you got the output SNR for BFSK system as a root rho max, which is equal to root of 4.84 EB by N naught. So I concluded that output SNR for BFSK system is more than BASK but less than BPSK. So we have increased BFSK output SNR over BASK, but it is still less than binary PSK. Now can any one of the student tell me what is the output SNR for BPSK and BASK? Already we calculated those in the last two classes. The previous classes we solved the BASK and the BPSK. Please compare the output SNR of BFSK with the BASK and BPSK. because that's we need. We need to compare all the digital communication, digital techniques. So keying techniques you need to compare. So please, any one of the student tell me what is the output SNR for BASK? So almost 52 students are there. Any one of you please tell me what is the output SNR for BASK system? How much we got?
Square root of 2 EB by N naught, ma'am.
Square root of 2 EB by N naught. That is for
BASK.
Okay. Can you tell me for BPSK?
Square root of 8 EB naught EB by N naught, ma'am.
Very good. So you can what you can conclude from that? How much you got for obtained from BFSK for BFSK?
Square root of 4.84 EB by N naught.
Okay. Now what you can say? What you can say as a conclusion?
For BPSK, output SNR will be high.
For ఒకసారి మళ్ళీ చెప్పండమ్మా.
For BPSK, output SNR will be high, ma'am.
Is high because it is root 8 EB by N naught. Which system has less output SNR?
For BASK, ma'am.
Because it is the root of 2 EB by N naught. But our our output SNR for BFSK is like in between the BASK and BPSK. It is more than BASK because it is 4.84, but it is less than BPSK. Okay, thank you. We can go to the next slide. So finally we concluded that the output SNR for BFSK is root 4.84 EB by N naught. This value is higher than BASK because for BASK output SNR is root 2 EB by N naught, root 2 EB by N naught, and but it is less than BPSK because for BPSK the output SNR is root 8 EB by N naught. So that's why the probability of error for BFSK lies in between. It's the intermediate value between BASK and BPSK. So let us go through the probability of error calculation. Now finally you obtained root rho max, that is x01 of t minus x02 of t divided by sigma. Now please substitute this value, substitute the value of root rho max in the probability of error expression for optimum filter. So you can write it as half ERFC of root 4.84 EB by N naught divided by 2 root 2. Divided by 2 root 2. Why 2 root 2 you have? Because already you have 2 root 2 in the denominator of complementary error function. So the same constant I mentioned here. Now let us simplify the probability of error expression for BFSK system. So here in the numerator you have 4.84 under root. So you can write it as 2. If you take this out, it will be 2.2 root EB by N naught divided by 2 root 2. So you, upon cancelling these two, you can get it as 0.77. You can make use of calculator and solve it. Did you get the same value? Please check it. Root 4.84 divided by 2 root 2. Please check the value. Is it 0.77? Check this value and tell me. Cheppandi. Did you get the value as 0.77?
Yes, ma'am.
Okay. Root 4.84 divided by 2 root 2, you will get it as 0.77. Okay. Now take this 0. Actually, all the functions, complementary error function should be like a root of the corresponding SNR. So that's why ERFC of root. So that's why take the 0.77 inside the root in order to represent the probability of error as half ERFC of root the factor of EB by N naught. Please take this 0.77 inside the root. If you take this 0.77 inside the root, you will get it as almost all 0.6. You can also check this. So take this 0.77 inside the root. So you can get it as 0.6 EB by N naught. You can check this. So finally, you can obtain the probability of error for BFSK system as half ERFC of root over 0.6 EB by N naught, where EB is the bit energy, which is PS into TB. Now what you can conclude? So please compare the probability of error for BFSK system with BASK and BPSK. I think already we calculated the probability of error for BASK and BPSK. Now any other student please tell me the probability of error expression for BASK. Ento chindamma expression cheppandi, one of the student. So 52 students are there. See, one of you please respond. K0 is there? K0. K0.
Yes, ma'am.
Can you tell me the probability of error expression for BASK, binary ASK system?
Half ERFC of square root of EB by 4 and naught.
EB by 4 N naught. If you take 4 to the numerator, you will get as 0.25 EB by N naught. Okay. Similarly, tell me the expression for BPSK. Mere cheppandi K0. Can you tell me the probability of error expression for BPSK?
Half ERFC of root or EB by and naught, ma'am.
Okay. Okay. What you can and how much you obtained for BFSK?
Of square root of 0.6 EB by n naught.
What you can conclude? Which probability of error is higher and which one is low? We have calculated the probability of error for 3 systems. Okay. So which system provides least probability of error, because we need to maximize the output SNR, then only we can get the least SNR, the least probability of error. So my question is, which system provides the least probability of error out of BASK, BFSK and BPSK?
BFSK is less than BASK, ma'am.
BFSK is less than BASK. ఎందుకని? Because if you observe the root over factor, here you have 0.6 EB by N naught. So here you are here this is greater than 0.25 EB by N naught. That is for ASK. Because EB by 4 N naught. So if you take 4 to the numerator, it will be 0.25 EB by N naught. But here you have 0.6 EB by N naught. So it means that the SNR is increased. So that's why the complement. So once SNR is increased over BASK, our probability of error will be less compared to BASK. Okay. Compared to BFSK, sorry, BPSK.
BFSK is more than BPSK, ma'am.
Probability of error for BFSK is more than BPSK. Okay. Endukani in BPSK you have half ERFC of root EB by N naught. Okay. So because it is EB by N naught for BPSK, SNR is more compared to BFSK. So once SNR is more inside the complementary error function, probability of error will be less for BPSK. So the final conclusion, okay ma, thank you. So final conclusion is that the system which out of BASK, BPSK and BFSK, the system which provides the least probability of error is BPSK, and the system which provides highest probability of error is BASK, and the system which provides high output SNR is BPSK, and the least output SNR is BASK. Our BFSK lies in between like the values of BASK and BPSK, but BFSK is less preferred because of its high bandwidth, because we need almost all 4 FP bandwidth, considering FH minus FL as 2 FP. Almost all the minimum bandwidth required to transmit a particular bit is how much? 4 FB in the case of BFSK system. So that's why in terms of bandwidth, or in terms of least probability of error, or in terms of highest SNR, PSK system is preferred over ASK and FSK. That's why we will have more applications for PSK over FSK and ASK. Even the MRA transmission techniques of PSK. So even if you see the MRA transmission techniques, our BPSK system still you can improve the transmission rate, as well as you can reduce the bandwidth by using MRA PSK. Okay, in terms of applications, BPSK has more number of advantages. It has least probability of error, highest output SNR. Now you can say what is the output SNR. So what is the output SNR for BPSK? Root 8 EB by N naught. What is the probability of error? Half ERFC of root EB by N naught. What is the bandwidth? 2 FP. What is the Euclidean distance? 2 root PS into dB. So 2 root EB, so which is a higher value. So Euclidean distance is higher, so our probability of error is less. That's why it is less. So like that, we have more number of advantages for BPSK. Now I request the students to kindly add these 2 points. Which points? Probability of error and output SNR equations in the tabular data which we studied in the second chapter. So please also add these expressions of BFSK, BPSK and BASK in the comparison table. Add the probability of error expression and output and SNR expressions of BASK, BPSK and BFSK in the comparison table which we studied in the second chapter, because you can add 2 more points. And even you can also add a root rho max also, square of output SNR. Not only root rho max, that is output SNR, you can also say the rho max, which is the square of output SNR. Okay, with this we can conclude the corresponding module 6, which is you can so each student can be able to derive the expression for output SNR and probability of error for BFSK system. Okay, in the next class we can discuss the probability of error calculation for QPSK. Okay, sorry, we can go through the corresponding thing. So in the next class we can let's see here. So we can calculate the probability of error expression by using the constellation diagram. Okay, so anyhow we can continue in the next class, no problem. So this is the last module of your third chapter. And one more thing I want to tell you is that already we discussed that the QPSK and BPSK systems have same Euclidean distance. That's why I told you that I told you in like a second chapter. I stated that because the Euclidean distance of QPSK and BPSK is same, because the Euclidean distance of QPSK and BPSK is same, the probability of error will also be same అని ఆ రోజు చెప్పాం మనం క్లాస్ లో. Okay, so that we can conclude here. So then what can be the probability of error for QPSK? Because the Euclidean distance of QPSK and BPSK is same, we discussed that the probability of error will also remain same. That's why we can say that the probability of error for QPSK is also same as that of the probability of error for BPSK. So it should be equal to half ERFC of root EB by N naught. That is our conclusion. So because the Euclidean distance of QPSK and BPSK are same, we can say that the probability of error will also remain same as that of BPSK. So BPSK, we know that the probability of error is half ERFC of root EB by N naught. So that's why the probability of error for QPSK also remains same, and it is equal to half ERFC of root EB by N naught, because the Euclidean distance for both the systems, what are the systems, BPSK and QPSK? As the Euclidean distance is same, the probability of error will also remain same. So we can solve it in the next class. With this, we can say that we can complete our module by tomorrow's class, so that we can finish our third chapter by tomorrow's class. And now I request the students to add these 2 points in the comparison table. The probability, you will forget. So now only you write down the 2 points. I will give you 2 minutes time. You write down the 2 points in the comparison table. I think in second chapter we mentioned the comparison of ASK, FSK and PSK. Okay, now please add these 2 points. What are the 2 points? Output SNR and the probability of error. Okay, please add these 2 points in the comparison table. So please take 2 minutes time for that and complete it. So meanwhile, I will take attendance. Complete the 2 points in the table of data. Write down the probability of error expression and output SNR expression in the comparison table. So otherwise we'll forget to write it in the material. Okay, please write down now, then we can stop the class. So did you complete? Okay, you can leave. I took attendance. You complete the 2 points in the notes and you can leave now.